Okay, so welcome everyone. This is lecture 12. We are getting very close to the end of the course of your introduction to quantum optics. I remind you that we are in a very crucial chapter of quantum optics, which is the theory of open quantum optical systems. And in particular, we are starting with the simplest example, which is an open optical cavity. So I remind you that we already did the theory. So we already developed a model for such a system in which we have a single cavity mode that is interacting through a partially transmitting mirror with the continuum of the electromagnetic field outside of the cavity. And then we studied that problem in the Heisenberg picture, and we saw that we can find equations only for system operators, for cavity operators, integrating out the external field. And these kind of equations are called quantum Langevin equations. So what we are going to do today is we are going to essentially describe the same problem, but now in the Schrödinger picture, with an evolution equation for the state of the cavity by, again, integrating out the external degrees of freedom. And we will see that we reach one type of equation that is known as master equation that plays a fundamental role in modern quantum physics, but especially in quantum optics. So then let's just jump into this subject. And as I said, we are going to start in the Schrödinger picture. And then this means that the first thing that we should do is write down the evolution equation for the whole state for the state of the whole system, including the external and internal degrees of freedom. So let me write it. So we know that the evolution equation will be a von Neumann equation for the density operator of the whole system, in which we will have the evolution generated by a Hamiltonian, and this Hamiltonian will contain the three pieces that we have been working with. So the cavity Hamiltonian, the external Hamiltonian, and then some interaction between these two. And as I say, rho is the state of the whole system, so including the external degrees of freedom. And just as a reminder, what are these Hamiltonians? So I remind you that the cavity Hamiltonian is just that of a free harmonic oscillator with a frequency omega c, which is a cavity, one of the cavity resonances, and annihilation and creation operators A and A dagger. Then we have the external Hamiltonian, which in the absence of interaction and so on, and this we already wrote as a sum over external frequencies, and we extended the frequency to minus infinity. This is unphysical artificial modes that we introduced in the theory and will play no role anyways. And then just h bar omega and b dagger b for each of the harmonic oscillators, describing a continuum of modes of continuous frequency outside of the cavity. And then finally, we have the interaction. In the interaction, I remind you as well that we wrote it with this phase, then some coupling. And the important thing that will come out today is that, and well, it already showed up in the previous lecture, that we chose a coupling that is independent of the frequency of the external modes. And this simplifies things enormously, okay? And we will see in more detail today what this simplification implies. And then what we have is just the possibility of tunneling. So we can create a photon outside of the cavity by annihilating a photon inside the cavity. And then the opposite process, which is just the emission conjugate of this one. Okay, so this is the starting point for for the theory in the Schrödinger picture. And then, as I say, our goal today will be to find an evolution equation for the reduced state of the cavity, which, as you know from our summary and our review of quantum physics with mixed states, this is just given by doing the partial trace over the external degrees of freedom of the total state. Okay, so we will call rho cavity to that state. So in general, this is a very complicated problem. So, I mean, you might think that it's just a matter of, okay, it looks simple. I just trace out and then I get here the derivative of the cavity state. And then I trace out that part in here and I write it in terms of the cavity state. But as you will see now, this is in general a very complicated problem. And it can be done only provided that we do certain approximations and that we keep track of effects only up to certain order in the interaction. So in particular, we are going to do this by considering effects only up to second order in the interaction, okay? More generally, second order in some Hamiltonian that it's small compared to a main Hamiltonian, so one perturbation of that. And for this, the first thing that we are going to do is moving to a new picture. And this new picture will require two changes of picture. So now follow me because it's going to be a couple of picture changes before we start with the actual derivation of the equation. But you will see that the pictures make a lot of sense, so that we are doing it for one special reason. So, okay. Let me start then with the first change of picture. So let me call it picture change 1. And the first change of picture is motivated by the following. So I remind you already from the last lecture that we already established that the external field, in this case at time 0, so at the origin of time, the external field will be a displaced thermal state. So this means that we have an environment, and this is the typical situation, that it's at thermal equilibrium, okay? And therefore is described by the thermal state that we know very well from the initial chapters. So the thermal state is just the exponential of minus the Hamiltonian divided by the partition function, which is just the trace of the exponential. But then we also allow for a number of lasers that can be driving the cavity. And these lasers are described. This is something we haven't proved. We haven't proved in the course, but it's something that is very well known in quantum optics, and maybe you will get to study it someday. That is that the presence of a laser outside the cavity, that means that you have a coherent part in the state, so a displacement on the state. And we are going to call D to this displacement. And let me just do something. I will call it D of 0, and you will understand in a second why I call it D of 0. Okay, for now, it's just a name, D of 0. You can imagine that there will come a D of T in a second. And this displacement is just the form of the displacement that you know that for any mode of frequency omega, we simply allow that it is displaced by a quantity alpha of omega. And then we get this displacement operator, multimode displacement operator. Okay, so I remind you that at the end of the day, what we will care about usually are lasers that are very narrow bandwidth, so narrow line lasers that are essentially monochromatic, and then we have lasers at different frequencies. So then at the end of the day, these alphas here, they will be 0 for almost all frequencies except for a finite number of them, okay? So we will see again with an example today this thing. So now, given this state, you can understand why we need to move to the picture that I'm going to describe. First of all, as we did in the Heisenberg picture, we don't like to have these displacements as part of the properties of the environment because they complicate the statistical properties of the environment. So we are going to move to a picture in which we discount these displacements. But in this case, it's even more important to do it. In the Heisenberg picture, we did it just for convenience. But here, it's really important that we do it because I remind you that we are going to do perturbation theory in the interaction. But for that, we need an interaction that is small compared to the cavity Hamiltonian, for example. Then this is not the case in general if you allow this B to have a mean value, to have an expectation value that is non-zero. So in particular, if it has a coherent part that can be arbitrarily large, so I can drive very hard with my external laser, then this interaction will certainly not be a perturbation, okay? So then the first thing that we need to do is that we have to discount that, that term, so that coherent background, I will call it, because we need to find a Hamiltonian, an interaction Hamiltonian that is just a perturbation over a bigger Hamiltonian. And then this is easily done. So for this, all we need to do is, as you can imagine, we just have to move to a new picture defined by a transformation, a change operator. So in which discounts, it discounts some displacement, okay? So we will do it quite general and we will allow this displacement to depend on time. So in particular, the displacement that will define the new picture, it's a unitary operator that will depend on some amplitudes beta that might depend on time. So they depend on frequency and they might depend on time. And then we have here the operators B and then minus B star, omega T, B of omega. Okay, so of course, the only condition that it's obvious is that this B of omega T at time 0, because we want this displacement to be exactly the displacement of the state, we know that this B of omega T at time 0, it has to be equal to alpha of omega, okay? So to the alpha that describes how many lasers we have outside and with what intensities, amplitudes, and so on, okay? So then in principle, given this, we have to, of course, we will choose a shape of this B of omega T, so a function of time that is the most convenient for the picture that we want to work in. And I will show you what is the best choice right now. So then in this picture, the new state that we can call, for example, rho D for displacement, is nothing but just the old state, rho, onto which we apply the inverse of the evolution given by d of t. So we apply d dagger t as the time evolution, and this discounts that part of the dynamics, and then it evolves according to the following Hamiltonian. So in general, I remind you that the Hamiltonian in the new picture, which in this case I will call HD, it's equal to just applying the same transformation onto the total Hamiltonian. So in this case, we have H cavity plus H external plus H interaction. So we apply the transformation, and then we have an extra term that is it comes from derivatives of the unitary transformation operator, which is this thing here. Okay, so this we already saw that when we move to a new picture, this is the Hamiltonian in the new picture. And what I want to, so I will not show it here, but you have it in the lectures, that if you just expand this expression in here, okay, you just do it carefully and you expand it. So you know how the displacement acts on, in particular, the B operators, because this is a unitary that depends only on B, so the part of A is untouched. But you know how the displacement acts on B. You know that it just changes it to B plus alpha. And at the same time, you can evaluate the time derivative of this operator. Okay, you can check it in the notes, but it's very easy to do it. And the time derivative of this operator will give you a piece that depends on derivatives of the beta. And then you will find an equation, or you will find a total Hamiltonian that depends on the choice of beta, and in particular, it depends on the differential equation satisfied by beta. So what you can see in the lecture notes is that if you choose the obvious choice, which is this one here, so at time t, we say that beta of omega t is just, so the displacement at time t is just the displacement at time 0, rotating with the frequency omega for mode omega. So this is just the amplitude of the coherent state that the external field is in at time t if there would be no interaction with the cavity, okay? So we just let the coherent state evolve freely according to the external Hamiltonian. So if you do that, then you find a very simple form of the final Hamiltonian, which is the following. So we get exactly the same Hamiltonian and one extra piece. So this is not going to be a surprise because we already encountered it in the Heisenberg picture. And this piece, this Hamiltonian, that I call it injection Hamiltonian, that depends on time, is something that you already know from the Heisenberg picture. In particular, this injection Hamiltonian, it's of time, can be written as just the following. This is A of t, and then A dagger minus A conjugate of t, A. And what is this A? This A is nothing but something proportional to the Fourier transform of the external laser amplitudes, okay? So you can see where this comes from. It's actually very simple, very intuitive. So when you apply the displacement, okay, when you apply this displacement to the interaction Hamiltonian, you will displace the B and you will transform it into B plus alpha of omega, okay? This means that you will get a piece in the Hamiltonian that is the same Hamiltonian, but now instead of the B operators, you will have classical amplitudes, alpha of omega t, okay? And that's exactly this Hamiltonian. I mean, if you look at it, this is exactly what you get, okay? The integration over omega, the B, so the alpha or beta of omega t, okay? And then multiplied by the square root of alpha over pi. So Then we see that this Hamiltonian that appeared very naturally in the Heisenberg picture to describe the external lasers, it also appears very naturally in the Schrödinger picture. And now what's interesting is that we have now a Hamiltonian in which we can really say that in particular this piece in here, so this part of the Hamiltonian, oh, sorry, no, didn't mean that one. I meant this part in here, so this interaction part. This, now we can say that it's small, or at least we can assume that it's small without being by definition incorrect, because before, if we would have said it's small, that's not true. But now we can hope that this interaction is rather small, okay? So this is the first picture change, and then the second picture change, it's much more easy. It's just a typical change that you do when you want to do perturbation theory. So we are going to do perturbation theory around this Hamiltonian, right? So our Hamiltonian now will be the basic Hamiltonian that describes the energy scales and so on, will be the cavity, the external one, and the injection one. And then we want to do perturbation theory with this interaction. So what we do is that we move to what is called the interaction picture, okay? So the second picture change, so picture change 2, which is nothing but interaction picture. So this will just be the typical interaction picture in which we simply discount the evolution generated or owed to the basic Hamiltonian, or the largest part of the Hamiltonian, which in our case is the cavity Hamiltonian plus the external Hamiltonian plus the injection Hamiltonian that has appeared in this picture, okay? So this means that we are going to use a unitary transformation to move to the new picture that needs to be the solution of the evolution generated by this time-dependent Hamiltonian. So then let me write down what this means. So this means that our time evolution operator will satisfy this equation here. And since it's the first time in the course that we deal with the time evolution generated by a time-dependent Hamiltonian, at least in terms of the time evolution operator, let me just say a few words. So in general, when the Hamiltonian depends on time, then the time evolution operator is not just the exponential of the Hamiltonian, okay? Divided by IH bar and multiplied by time. So you need to find the solution of this equation. And I already wrote in the lecture notes, so you will have them probably tomorrow, a little bit about this kind of time evolution operators. But hopefully, at least in your perturbation theory classes in quantum mechanics, I hope that you have seen that for time-dependent Hamiltonians, you can solve this solution. You can solve this equation for the time evolution operator with something that is called the Dyson series. Or the Dyson expansion, and that you can write in a very compact form in terms of time ordering expressions. So in particular, you would do the following. You would say, oh, the solution of this, if this would be just numbers instead of operators, then you would say that the solution of this equation is just the exponential from 0 to t of dt prime, and then the Hamiltonian of t prime divided IH bar. But we have here a problem, which is that it's not ensured that the Hamiltonian at different times commutes. So this is not the solution of this equation, okay? And the solution of this equation, you have to do one more thing, which is you have to time order this expression, okay? So this symbol here is what we call the time ordering symbol, okay? And what it does is it simply orders whatever operators, product of operators you have, it orders it in chronological order starting from the right, okay? So if you have a product of two operators, one at time 0 and one at time t longer than 0, then the time order of that expression will always be first the operator at 0 on the right, then the operator at t on the left, okay? So if I give you the product in converse order, so I say 0t, and then I apply the time ordering operator, it just inverts it, okay? So I hope that this is something that you have seen in quantum mechanics, but in any case, it's not so important for us, but I want to mention it so you know that this is actually the general or the typical time evolution operator in quantum mechanics, okay? So whenever you have time-dependent Hamiltonians, which happens most of the time because you always move to a picture in which we discount part of evolutions and at the end the Hamiltonian becomes time-dependent, you always get this kind of time evolution operator. In our case, it's especially simple to write down this Hamiltonian because we know the explicit time dependence of the Hamiltonian. So it's this thing in here. So it depends, the Hamiltonian depends on time only through these functions A. So not because the operators themselves are Heisenberg picture operators or anything like that. It's just because these functions depend on time. And therefore, this integration can be done explicitly. So we can carry out the integral. And then once the integral is carried out, we get the following expression. We get minus omega c t a dagger a. So this is the part that comes from the cavity Hamiltonian. Then we have the part that comes from the injection Hamiltonian. And this is very easy. It's just some function of time, a dagger, and then minus the same function of time conjugate a. And this function of time, as I said, is nothing but the integral of the function that appears in the injection Hamiltonian. And then finally, we get also the exponential of minus I t, and then the external Hamiltonian. Oops. So let me move this a bit. So we get the b dagger b. Okay, and now I can remove the time ordering operator because now I don't have any operators that have time dependence. So all the time dependence is in these factors here. And now this expression is fine. So time order or no time order, this expression is already time ordered. So as I said, I hope that you are a bit familiar with these things, but just in case, I let you know in more detail. So then let me just do one more thing because I will maybe need the space. So let me put this above. So this is a time ordering. Okay, so now that we have the picture, or the unitary operator that defines the picture we want to move to, then the state in the interaction picture, which is nothing but discounting this evolution from the previous picture that we come from. So I write it in terms of the original one. So we already discounted a displacement. Then this is the original state. Okay, then evolves according to the following Hamiltonian. So this Hamiltonian is just the Hamiltonian in the interaction picture. And just by definition of changing the picture, this is just the unitary transformation applied on the Hamiltonian. So of course, the Hamiltonian from the picture we come from. So this is the HD. Okay, minus IH bar, UC dagger, and the time derivative of UC. But now this is a very, very simple expression because you see that the time derivative of UC is actually, you see it here, is H0 times U. Then we have U dagger. So this means that in total, what we will have is just UC, okay, so the transformed, and then we have the Hamiltonian that we have minus H0, okay, extremely simple. So we just take the Hamiltonian that we have and we remove the cavity, the external, and the injection Hamiltonian. This is why we define this, the unitary transformation with this Hamiltonian. So in total, we get that the Hamiltonian in the interaction picture, what we can call the interaction picture Hamiltonian, it's just the interaction Hamiltonian transformed. Okay? So this is the final form of the Hamiltonian, and we can write it in more explicitly in the following way, because we know the following. Maybe I will need the space. So we know how the transformation acts on the B operators. So in particular, from the point of view of the B, the unitary transformation, it's only what? It's only exponential of minus IT omega B dagger B. So you can, I mean, you know it already from several times that we have used it in class, but if you are not convinced, you can use the Baker-Campbell-Hausdorff lemma, and you will get that the transformation simply rotates, so makes rotate in time the B operators. On the other hand, the transformation applied on the A operators, so it's also possible to find what is the explicit form of this operator as a function just of A and the parameters of the transformation, because this transformation is also very simple. It's just a displacement and a rotation, but we don't need it. So we will not need it. So what I will do is that I will just define this as the interaction picture annihilation operator. So AI of T, okay? We don't need the explicit form of this. So then taking these two things into account, the final form of the Hamiltonian in the interaction picture is this very simple one. So it's just the one that we have, in which we had the interaction of B dagger omega with A, but now the A is the one in the interaction picture, and the B dagger of omega is multiplied by I omega T, okay? And then the same for the other part. So for the Hermitian conjugate. Okay, so as I say, this is the final form of the Hamiltonian. In the final picture, we are going to work on. Okay, so let me write it down. This is the interaction picture Hamiltonian. And everything is ready now because we are working now in a picture where the full Hamiltonian is just the perturbation, okay? So now we have a Hamiltonian that is really small. So all the Hamiltonian can be considered small. So now we can start doing perturbation theory. So let me write down again the von Neumann equation in this picture. So for the von Neumann equation in the interaction picture, so of course, this is equal to just IH bar and then the time derivative of the state in the interaction picture. And this evolves according to the Hamiltonian in the interaction picture. And what's important as well is that I give you the initial condition. So the initial condition of the state in the interaction picture, this is equal to whatever initial state you have in the cavity. This is not so relevant, as you will see. And now what is relevant is what is the state of the environment. And the state of the environment, so you just have to look at the picture we come from. So the original one, the original external, is just the displaced thermal state. Now, after the first picture change, we have discounted already the displacement, and we are left only with the thermal state. But now, on top of that, we have made the transformation U dagger U, okay? But this U is just a rotation, and the thermal state is invariant under rotations, okay? So this transformation leaves invariant the thermal state. So you saw already in chapter 2 that thermal states are like a circle in phase space, and then no matter how you rotate it, is the same circle. So then the state in this picture, it's still a thermal state for all the modes. And then we make the approximation that all the modes have the same excitation number, so thermal number of excitations. And this is what we did already in the Heisenberg picture, okay? So this N is just the Bose-Einstein distribution at the frequency that we are working at. But we assume that this is more or less flat around the cavity resonance. And therefore, this is just the Bose-Einstein distribution at the cavity frequency, okay? So this perfectly defines the starting point for our perturbation theory. And now you can do a formal perturbation theory, but I will show you now a trick to get it kind of faster, which is the following. So we have here an expression that depends linearly on the interaction Hamiltonian. So what I am going to do is now I am going to find an expression that depends, so it's equivalent to this equation, but depends quadratically on the Hamiltonian. Then once we have an explicit expression that it's already quadratic in the Hamiltonian, it will be very easy to see which kind of perturbation theory or which kind of approximations we need for keeping terms only up to second order. So, and this is done very easily in the following way. So let me write it in the following. So we are going to find a more convenient form for perturbation theory. And we do it in the following way. First of all, I just formally integrate the von Neumann equation. And if I formally integrate the von Neumann equation, I get the following. So this is just the integral form of the von Neumann equation. I didn't do anything, just integrate it. okay? And now, if we insert in the von Neumann equation again, so we insert this back in the von Neumann equation. So what I mean by that is that we take this rho I of t and we just put it in here in this commutator. So we get this thing in this part of the commutator. And I already take, because we are interested only in the cavity state. So we already take the trace over the external modes. What we get is just the following equation that is ready for perturbation theory. So let me make sure I have space. So we get, when we take the partial trace of this expression, the partial trace can go inside of the derivative, and then we get here the cavity state. But careful in the interaction picture, okay? So I write it explicitly. And then this is equal to, and now we get two terms. So when we have this part in here and we put it in here, we get one that depends on the initial condition. And this gives us 1 over IH bar. And then the external, so the trace over external modes. And now we get in here the commutator of H with the initial condition. Okay? So this part, as I say, it comes from this part of the formal integration. And then now we have the part that comes from the other part of the formal integration that I can write as 1 over H bar square. And then we have the time integration. And now we will have the trace over the external modes. And then we have a double Hamiltonian commutator now. First, the commutator with the Hamiltonian. And now the commutator that we have inside of the formal integration, which is another Hamiltonian, but in the integrated variable. And then the state, also in the integrated variable. Okay? So this expression here, it's exactly equivalent. So we haven't done anything but just we have rewritten things. It's equivalent to the von Neumann equation, but now you see that it depends explicitly on second order terms in the Hamiltonian. Okay, and moreover, let me just say that this piece in here is going to be 0. And why it is 0? So the idea is the following. So let's just see what's inside of this partial trace. So we have here what? We have the interaction Hamiltonian multiplied by the density operator at time 0. But the density operator at time 0 for the external field is just the thermal state, right? And the interaction Hamiltonian is linear. So I show you again. The interaction Hamiltonian is linear in the B operators, okay? So then at the end of the day, this whole term in here can be written as something proportional to expectation values of the B operators in the thermal state. And what is the expectation value of the annihilation operator in a thermal state? So just remember, the thermal state is where? It's at the origin of phase space, right? It's a circle bigger than the circle of vacuum in the origin of phase space. So this means that the expectation value of X and P, or the expectation value of B, it's actually 0, okay? This we already saw in chapter 2. So then this whole term, so this term that depends on the initial condition is 0, okay? And on the other hand, in this expression, I will just make one convenient variable change, which is I change t prime by t minus tau. Okay, just a variable change that simplifies a bit the expression. And then finally, if I take these things into consideration, the final equation that we get for the cavity state at time t, it's equal to 1 over h bar squared, and then the integration from 0 to t of the new integration variable tau, and then we have the external trace, and then the double commutator with the Hamiltonian, first at time t, then at time t prime, which now is t minus tau, and then commutator with the full state at time t minus tau. Okay, so why did I make the variable change? Is just because now you see that, so let me remark it. Now you see that essentially the state at time t depends on the whole history from time t to time t minus tau, but tau goes through the whole history from 0 to t, okay, of the previous stages. And this means that this is so first of all, it's an exact equation. So we still didn't do any approximation. We just rewrote the equation in a more convenient way. But it's important that this equation is not Markovian. Okay. Non-Markovian means that it has memory. So the evolution of the state at time t depends on what happened not only at time t, but what happened before. So on the history. Okay. So it has some memory, and that we call non-Markovian. Things that do not depend or do not have memory, we call them Markovian. And this is an equation that is integral differential. Okay, so it looks like we have complicated things a lot. Okay, because we have now a non-Markovian integral differential equation, but at least it's an equation for the reduced state. Okay, so this is the exact form of the equation for the reduced state. And of course, as you can imagine, now we are going to make some approximations that will turn this exact non-Markovian integral differential equation into an approximate equation that it's Markovian and it will not be integral. Okay, it will just be a differential equation. And this will be the master equation. So I think that before we enter into this approximation, we can make a short break. It has been already 50 minutes or something like that. So maybe let's regroup at 2:55, okay? See you in a second. Okay, so welcome back. So now what we are going to do is we are going to make a few approximations. And in particular, as you see on this side, we already have what we want, which is the time derivative of the cavity state. But on this side, we have the full state in this equation. And then we would like to somehow bring this external, so trace over the external degrees of freedom inside. So we get in here also the trace over external degrees of freedom of the total state, and then this becomes the cavity state. So this is what we are going to do right now. Of course, we cannot do this at the moment because this Hamiltonian, it also depends on operators of the environment. And therefore, if you just trace out and of the system as well, so if you just trace out, you will have to trace multiplications of the full state by operators of the system and the environment. And this is what we are going to do, or what the approximations will allow us to do easily. So in particular, as I already mentioned, the approximation that we are doing or we are going to make it's just a very basic one. It's just we are going to neglect effects of order Hamiltonian to n larger than 2. Okay? So this is what we will do. So you might ask me, okay, but this is a bit weird because we have an equation that it's already quadratic in the interaction Hamiltonian. So how can we make it more quadratic? I mean, it's already quadratic, right? But actually, it's not true that this equation is just quadratic in the Hamiltonian because there is an implicit dependence on the Hamiltonian also through the total state. Okay, and this is what I am going to show you now and how we can approximate or remove this higher order dependence of the state. So in particular, to see that we indeed have this kind of dependence, just imagine what is going on. So at time 0, the state of the system is just this uncorrelated state in which we have the cavity state at time 0 times the environment state, so the external state at time 0. Okay, this is the state initially. We don't have correlations between them. Now we apply evolution. So we apply evolution means that we apply the time evolution operator, and the time evolution operator for this time-dependent problem. Now you know very well that this is equal to just the Hamiltonian divided IH bar, and all this is in time order. So the explicit expression is not very important. All I'm saying is that if you want to evaluate the state at some time t, you have to apply the time evolution operator, and the time evolution operator will induce the generation of a new state that now has correlations between the system and the environment, between the cavity and the external modes. So what I mean is that this state is not of this type. So it's not the state of the cavity at time t times the state of the external field at time t. We cannot write it like this. We will generate some correlations between them, but the point is that these correlations, so anything that deviates from this kind of state, okay, will be at least of order interaction Hamiltonian, okay? And in particular, so what I am saying is that H, the interaction Hamiltonian, induces correlations, but these correlations are at least of order Hamiltonian. So then something that we can do is that we can assume, so we can make the approximation that this is approximately correct. So the interaction Hamiltonian is approximately an uncorrelated state of cavity and external field. So we make this approximation here. This is called the Born approximation. And it's essentially neglect correlations between the system and the environment, between the cavity and the external field, okay? So this is the first approximation that we can make. So we decorrelate the states of the cavity and the external field because we know that this will contribute to this equation with something that it's beyond 0 order in the Hamiltonian. And since we already have a quadratic order here, we don't care about that. On the other hand, we can make one more approximation that it's also, it's a bit independent of this one, but it's also connected, which is that is the following. So the environment So it is clear that the environment has a huge impact on the system, on the cavity. Okay? But, and here comes the approximation or the motivation for the approximation. The converse is not true, so not the other way around. Okay, and let me explain this in a bit more detail. So all I'm saying is the following. So we have an environment. Okay, so we have here an environment, which is a huge system. So this is a system that has infinitely many degrees of freedom. So it has many harmonic oscillators, okay? And that form a continuum. So it's all the free space outside of the cavity. On the other hand, we have a very tiny system. So the cavity, and as I say, this is very tiny, very tiny compared to the huge environment. And at the same time, the interaction between these two, so this interaction Hamiltonian, it's actually small. Or we are assuming that it's small. Then it makes sense that a huge system interacting weakly with the small system, with the tiny system, makes an effect. But what's not to be expected is that this tiny system interacting very weakly with a huge environment makes a real effect, like a very strong effect. And therefore, we can make the extra approximation that the external state at time zero, sorry, not at time zero, but at any time, can be approximated by just the state that we had at time zero, which is the thermal state. Okay? So this is the second approximation. And we call this that there is an absence of back action from the system to the environment. So the environment acts on the system, but the system doesn't back act on the environment. Okay? So we have these two approximations that together combine to the approximation that the state of the whole system, we write it as some uncorrelated state of the cavity times the thermal state of the environment. Okay, so this is called this is essentially an approximation that neglects effects higher than second order in the interaction for this equation, and I usually split this in the Born approximation, that is this uncorrelation, and the absence of back action. But in many books and many people call Born approximation to the whole thing. Okay, so I just want to let you know that these are two levels of approximations that are slightly different. And actually, you can try to do a theory. This is what I have, for example, in one of my papers. You can do a theory in which you do this approximation, but not this approximation. So you still keep the effect of the system onto the environment. And this is important when you are trying to trace out a system interacting with another system, when the two systems are kind of the same size. So you cannot claim that one system is very big and the other one is small, okay? Even in that situation, you can still try to find an equation for a reduced system, but now you cannot make this absence of back action approximation. You have to do the Born approximation only, okay? So you will see now that with these approximations, now this equation is very simple. It turns into something very simple. But before that, I just want to make a very, very important remark, okay? And this remark is very important because this is a typical misconception of people working in master equations. It's very important that you understand that we are not saying okay, so this is a not thing. We are not saying that the state of the total system is this. So we are not saying that the total state is equal to this. Okay, this is very important. If someone asks you, what is the state of the system? You cannot claim that this is the state of the system. What we are saying is that deviations from this state enter the dynamics of the cavity, okay, to an order that is higher than second order. That's what we are saying. So we are talking about approximations of the dynamics of the state of the cavity. But we are not claiming that the state of the full system is this state in here, okay? That's true only from the point of view of the dynamics of the cavity, okay? So let me write it down. So we are not saying that the state of the full system is this one, but only that deviations from this state contribute as order Hamiltonian to n larger than 2 to the time derivative of the cavity state. Okay? So this is a very, very important remark. And actually, we are going to see that the state of the cavity, so I give you two reasons why this is not the state of the system, or we are not claiming that. The first thing is that, and you already know this from the Heisenberg picture, that the state of the cavity, in general, it will be a mixed state, okay? So the equation that we find at the end will tell us that starting from any state, for example, from a pure state, maybe the cavity was initially in vacuum or whatever, then the evolution will drive you into a mixed state. In particular, for long times, you will be in a thermal state, as we saw in the Heisenberg picture. But how is it possible that you start from a pure state and you end up in a mixed state? The only possibility, because the whole system is closed, is that you create correlations between the system and the environment, okay? And this is very clear because the state is mixed. So therefore, this is not the state of the total system because we really have correlations. It's just that we don't know how to describe them. So we don't know how to analytically write the correlation part of this state. We only know how, when you trace out the environment, you are left with a mixed state of the system. And then the second thing that we will see in the next chapter is that actually, even the external state, okay, so the field that comes out of the cavity will have quantum properties such as squeezing or something that we will call anti-bunching. And these things are different from a thermal displaced state, which means that the state that comes out of the cavity, so the state of the external modes that are coming out of the cavity, is not the original thermal state, okay? We will see that these things appear in the theory very naturally, but all these things are effects that do not need to be described to second order in the dynamics of the cavity. That's all we are saying, okay? So after this remark, then we can continue with the...
Sorry?
Yes.
What this, it seems even if you make the approximation, it's and the effect is still beyond the second order, I think.
If you make what approximation? Sorry, I cannot hear you well.
The approximation made here.
Yeah.
It's already beyond the second order, I think, because there are already two HI in this evolution.
No, but that's not true. It's what I am telling you. This, sorry, this part in here.
Yeah, it evolves according to HI, right?
Exactly. So then this thing in here, it also contains powers implicitly. It's not explicit, but it contains powers.
Yeah. So if you are just interested in second order, then you can take rho I to be rho I zero, the initial stage.
You mean rho I of t is enough, because this is rho of t. So this also contains already, so this part of the expression already contains some order in the interaction, right? Because this is rho of t.
Yeah.
And here, if you keep this at time t and you make this separation, okay, you also consistently get second order only. Okay. Yeah. So this is telling you that so you will need different types of approximations. Okay. So let me put it this way. This set of approximations that I have given here, this is clearly giving you second order, right? That's completely true. So if you make these approximations, then what you end up with, it will be second order. And you will see that actually these approximations already imply, just by themselves, that this will be evaluated only at t, not t minus tau. You will see it now in the derivation. I don't have to assume that this depends only on t, not t minus tau. Okay? This will come naturally from these approximations. Okay? But it's not true, the opposite will not be true. If you just make the approximation that this doesn't depend on tau, okay? I agree that...
You just take the rho I t minus tau to be the initial state, rho I zero.
No, but that's inconsistent, because this expression here already depends on t. This means that this expression here is already depending on some order on the interaction, because this is the state at time t, it has evolved, okay? Then in here, you have to keep the interaction, at least you have to keep the time t, not t minus tau, not 0, but t.
Okay, so
okay?
So it's
then in that way you know that this thing is correct. However, what I am saying is that this will happen naturally. It will happen now with these approximations. Okay.
Okay.
If you would make this approximation by hand, you would say, oh, I will just make the assumption that this tau is not there. Okay.
Yeah.
You will still have to make this approximation, this Born approximation. You will need to do a separation, because otherwise you will have an effect, because all you are saying is that the total state you evaluated at time t, but you are still allowing for correlations between the system and the environment, right? At time t. So you have to make this approximation, and you have to make this approximation still in order to keep second order effects in the time derivative. okay?
Okay.
So, but you will see now that we don't need to make that approximation because these approximations already contain it. And I will discuss why, and in the next class, we will see what happens when you don't assume that approximation that leads to that, okay? So let me just continue. I think I will convince you of this, and otherwise you can ask me again at the end, okay?
Okay.
Okay,
That's
so
good.
I show you because now what is left is really simple. It's really just including this expression. So in particular, including this expression into the following part. So the right-hand side of the equation. So with this approximation, or rather approximations, then the term on the right-hand side, which reads like this. So let me write it down again. So it's the term that we were discussing, is the double commutator of the Hamiltonian with the state. But, well, let me now write the state in the following way. So this is the cavity state at time t minus tau. And then for the environment, we keep just the thermal state. So this is now the right-hand side of the equation. And now you see that this thing in here, it's equal to, well, let's count terms. So we have Hamiltonian, Hamiltonian, and then we have external trace, and then this is already a tensor product. So at the end of the day, we will have the trace, the external trace, the product of operators in the external space given by the Hamiltonians, and then the state of the external modes. So in particular, because the Hamiltonian is linear in the B operators, okay, then what we will get are objects that will be quadratic in the B operators, and then the expectation value in the external thermal state. So how many terms do we get of those? We get 16 terms just because we have a double commutator. So we have 4 terms already. And then each of the Hamiltonians has 2 terms. It's a sum of 2 terms. So I remind you here, this one and this one. So in total, we will get 16 terms, but all of them, so we get 16 terms, but all of them will be proportional to external second order moments, okay? And in particular, I mean external second order moments, I mean the expectation value of operators B at 2 different frequencies in the thermal state, and the external trace again, so expectation values of, for example, B dagger B, in the thermal state, okay? And we will also get states in which this is B and this is B dagger, and also states in which both of them are dagger. Sorry, terms in which all of this is B dagger. So now you know that for a thermal state, the second order moment that has BB or B dagger B is equal to 0. Go to chapter 2 and check it if you don't remember. But again, it's the same argument. We have a circular state in phase space, and this B operator and B square operator, it is not phase invariant. and therefore the combination of these two things needs to be 0. And on the other hand, this term in here, it will be just proportional to the number of excitations, but only if you are working at the same frequency. So this is the same that we saw already in the Heisenberg picture, and that we saw in chapter 2 for a single harmonic oscillator. And this is for B dagger B. If we have B dagger, because of the commutation relation between B and B dagger, then we will get the same kind of expression, but here an n+1. Okay? So then we will get 16 terms. All of these terms will be proportional to one of these second order moments. And therefore, we know how to handle them. And in particular, let me show you explicitly 2 terms, okay? I show you 2 examples. So let me just show you these examples. So for example, we get 1 term. So let me show you which one I am going to consider. Imagine that I am checking the first term of everything, which is hi times hi times the rho. And out of the hi, so out of the multiplication between hi's, I consider this term times this term, okay? So then I consider this term times this term times the state. That's one of the 16 terms, let's say the first one, okay? And this gives me the following. This gives me gamma over pi, because the interaction has a square root of gamma over pi. And then we will have the integral over omega, the integral over omega prime. And then we will have the multiplication of the A operator with the A operator at t minus tau, and then with the cavity state at t minus tau. And then we will have, so I remind you, the Hamiltonian has these exponentials and then the b's. So this brings me to I omega t plus I omega prime t minus tau, because one Hamiltonian is at t, the other one is at t minus tau. And then finally, the trace over external modes of B dagger of omega with B dagger of omega prime, and then expectation value in the thermal state. Okay, so this kind of term, because as I have said, this is 0, this type of term will be equal to 0. Okay, so these kind of terms that are proportional to 2 annihilation operators of A or 2 creation operators of B, this will be equal to 0 automatically. On the other hand, we will have other types of terms. For example, the one I'm going to write. So now I will consider, let me see. I will consider now, again, the same multiplication, h rho, but now h have 2 terms, so I consider the A term of this one and the A dagger term of this one, okay? So I will consider the multiplication of this term with this term. Then we get the following. We get now AI of t, AI dagger of t minus tau, and then the state of the cavity at time t minus tau, then the exponentials. So the first exponential is just the same as before, and now we have the opposite sign for the other one because it's A dagger. Oops, t minus tau And then finally, we get here a trace over external modes. And now we will have B dagger of omega, B of omega prime, and then the thermal state of the environment. Okay, but now this is not zero. This, as I have written there, this is the number of excitations times the delta function of omega minus omega prime. This is very nice because now one integration over omega, we can remove it. Oops, I actually wrote only one. That's why I had so much space. So of course, we have the multiplication of two Hamiltonian terms. So we have the double integral omega omega prime. Then, as I was saying, this delta function will remove one of the integrals and we make it that omega is equal to omega prime. So if we check the exponential, then all that is left in here will be the following, will be gamma over pi. And then we get, well, gamma n over pi. Then we get the integration over omegas. But look in here, all the information about omega is contained in this function. Nothing else depends on omega. And then we get what we already had. So A dagger, T minus tau, and then rho cavity, the interaction picture at T minus tau. So let me bring it down. So, but now you see that this thing in here is nothing but 2 pi, the delta function of tau, okay, the delta function of time. And here is where you see that actually, just from these approximations that we have made, we already get the time locality, okay? So now we get here a delta tau that when we come back to the original expression and we have here the integration from 0 to t, this delta tau, which means that tau is equal to 0, okay, removes the integration and tells you that you only care about the state at time t. You see that, Sijan? So that appears very naturally just from these two approximations. And you can trace it back even to before, okay? Because the reason why you get here just this integration of omega of the exponential is because we have made the approximation that the interaction doesn't depend on omega, okay? If the interaction, which is contained in this gamma, the interaction between the system and the environment, would depend on the frequency, this would not be a delta function. This would be an integration of the exponential, so it's a Fourier transform, if you want, of the coupling of omega, okay? And this Fourier transform is not a delta function in general, if it depends on the frequency, okay? So we see at this level that the approximation that we made, that gamma didn't depend on omega, that can already be seen as what we will call a Markov approximation, okay? So this equation is in principle non-Markovian, but together with the Born approximation, it becomes Markovian if the coupling is assumed not to depend on the frequency. So in the next lecture, we will work also with the open theory of an atom, okay? And there we will relax this condition and you will see what happens when the interaction depends on omega, okay? And you will see that we need to make this approximation by hand. Just these approximations are not enough to allow you to assume that this derivative depends only on the state at time t, okay? It doesn't depend on the history, okay? So then whatever, mathematically, at the end of the day, what we get is that this type of term becomes something like this, just proportional to the delta function in time, And then we can write all the operators at the same time now, because tau is 0. Okay, so if we proceed in the same way, with all 16 terms, so with the other 14 terms that I didn't write, and we also used that the integration from 0 to t of d tau of any function of t minus tau and then delta tau, this is equal to f of t divided by 2. So I remind you that divided by 2 comes just from the fact that this delta function tells you that tau is equal to 0, but tau equals 0 is already in the edge of the integration domain, okay, in the boundary. So then you have to put factor 2 for any function that is continuous. And then with this thing here, you find the final form of the master equation that takes this shape. So I don't write time dependence now, just because you see that now all the time dependence is local. So it's time local, it's Markovian, it's everything at time t. And then we get this expression here. So don't worry about how long it is or whatever, because you are going to get very familiar with this type of expressions, as we will discuss in a second. So we get the following. So let me write it down. So we get this term, and then we get another term that is proportional to n gamma directly, and it's the same. So I will copy it. It's exactly the same term, but exchanging the daggers of the a's. Okay. So this is the final. So you can count the number of terms. Okay. How many terms do we have? 2, 3, 4, 5, 6, 7, 8. So we get 8 terms. So 2 times 4 that are non-zero. And then because they are proportional to this kind of operator, B dagger B or BB dagger, and then we get 4 that are 0, sorry, 8 that are 0, because we have them proportional to either B dagger or BB, okay? Which makes sense. We have half and half. So in other words, if I just, so this is the equation for the cavity state. And you see that now it's an equation that depends only on the cavity state and it's time local. But let me now come back to the original picture, because this is in the interaction picture. But now I can just come back to the original picture, just doing undoing the transformation. So coming back to the Schrödinger picture. So this means that we are now transforming from the cavity state in the interaction picture. We apply the UC transformation. Okay. And then if you just use this transformation, you get back to what you expect, which is that the cavity state, it's equal to, first of all, the Hamiltonian in the Schrödinger picture, which contains the cavity Hamiltonian, plus the injection Hamiltonian, and then divided by h bar. So this is the von Neumann equation of the cavity. And then we get the two terms that come from the tracing out the environment, which is 2a rho cavity, a dagger, minus a dagger a rho cavity, minus rho cavity a dagger a, and then plus n gamma, and the same, but exchanging a dagger with a. Okay, so this is the final form of the evolution equation for the reduced state of the cavity, and this is known as the master equation. Okay, so as we have discussed, so I will give you now more interpretation about what is the meaning of these terms and so on. But the first thing I want to discuss about this equation is, first of all, it's time local, or as I told you, this we call Markovian. And I just discussed why this happens. It happens because we already made one approximation that is very good for an optical cavity, so that the coupling doesn't depend on the frequency. But if you cannot do that approximation, then you don't get a Markovian master equation. You have to impose one more approximation, which is a Markovian approximation. And we will see that in more detail when we deal with atomic open systems. Then the second thing I want to mention is that, of course, you can, just like we did in the Heisenberg picture, you can include any intracavity Hamiltonian that you want. So maybe an atom interacting with the cavity, or a nonlinear dielectric inside the cavity, as long as this Hamiltonian, this intracavity Hamiltonian, is just a perturbation, okay? Okay, and the idea is similar to what we already saw. Like, we already saw that if the intracavity Hamiltonian is too large, then you change the spectrum of the Hamiltonian that you are considering the bigger part of the Hamiltonian, and therefore you cannot do just these approximations in which you only consider modes around the cavity frequency and so on. You have to really consider the full spectrum of the Hamiltonian. Okay. So these are the two simple comments I want to make here. And maybe we can do now a final break. And then I will give you in more detail some properties of these equations, including like, why do they have this shape and what do these terms mean and so on, okay? So let's do a 10 minutes break and we meet at 2:50 again. Okay, so let's continue with the final part of the class. So the idea now is that, so we have found this master equation for an open optical cavity. Okay, it's very nice, but we have found some kind of terms in here that actually both terms look very similar, just replacing a by a dagger. So I want to discuss a bit about why do we find this form, or in more generic terms, is this a generic thing in open quantum systems? So we will always find this kind of form for open quantum systems. And also, what is the meaning, the exact meaning of these terms, okay? And then we will go to one example, the same example we did in the Heisenberg picture. Okay, so Then the first thing I want to mention is that this form is actually a very common form. It's called Lindblad form. Lindblad. Okay. So this kind of master equation that I have written, we say that it has something called Lindblad form, which is Lindblad is a scientist who developed these kind of things, I think, in the 70s. But the point is that this is a common form. So this always happens, okay? Any open system has this kind of evolution equation. So this kind of master equation, but only if you are in the Born Markov approximation. So if your system satisfies the Born and Markov approximations, so this time locality that we talked about, and that you can find an interaction Hamiltonian and truncate to second order in that Hamiltonian, then under Born Markov approximation, the master equation always have this form. So it's possible to prove that any open system under the Born Markov approximation for the interaction with the environment will always be described by an equation that has a Hamiltonian part that includes the Hamiltonian of the system and any renormalization or change induced by the environment, like for example, the injection Hamiltonian. And then it will have terms with some rates, kappa j, and all of them will have this form. So this is not an accident, okay? All of them will have this form in which you have 2 times j rho j dagger minus j dagger j minus rho j dagger j. Okay, so I'm not going to prove this, like proving this will take some time and it's a bit technical and a bit beyond the scope of the level of the course. But you can prove that any open system under the Born-Markov approximation for the interaction with the environment can be described by a master equation that has this form, Hamiltonian terms and some, we call it dissipative terms, with some rates kappa j and some operators j. We will call these operators the jump operators. You will understand in a second why we call it jump operators. Okay, and this is something that appears so often that we actually give it a name. So we call it D, and we put the subindex J. So this means that this whole form, okay, we call it D, and then the operator that defines the form. And this can be seen as a map that acts on states or on operators. And we will call this thing the dissipative superoperator. Okay, we call it superoperator to this D because it is a map that takes operators, rho, and maps it into another operator that is this complex operator here, like j rho j dagger minus j dagger j rho minus rho j dagger j. So in that sense, it's a superoperator. It's an operator that acts on operators, okay? Actually, this is, so at this point, it just looks like, okay, fancy terminology, fancy way of calling things, but this kind of vision of operators acting on the space of operators, it's actually the way in which is the vision that motivates the most efficient kind of methods, numerical methods that we have to solve master equations of this type. So We will not have time to go through this in the course, of course, but probably in my notes, you will find it at some point how to deal numerically with this kind of system. And I already have something on archive for this. So if you are interested, I will put the reference in the notes, and then you can see how from this super operator picture, you can develop numerical coding and numerical tools to solve master equations. And in particular, usually the whole master equation, we represent it. So the whole right-hand side of the master equation, we represent it with a super operator that we call L. And this usually is called the Lindblad super operator. Or maybe you have heard the word Lindbladian, okay? So essentially, at least this allows you to see that this form of the master equation that we have found, and of course in our case, so let me just explicitly write this, that in our case, we have two J's, okay? One with rate n+1 gamma, and the corresponding jump operator, so J1, it's equal to A. And the other one, kappa 2, it has rate n gamma, and then the jump operator J2, it's equal to A dagger. Okay? So our master equation is exactly of this type with two jump operators and two rates. So, and now you know that this is not an accident. This happens every time that your system satisfies Born-Markov conditions with the interaction with the environment. Okay. But then now let me go deeper and try to understand what is the meaning of this kind of term, which is the new kind of term that you find in these equations. So this equation, these master equations, is just a von Neumann type of equation that you know very well. It has all the quantum coherent effects that we love so much. And then it has new type of terms that we still need to understand, okay? So that's what we are going to do now. We are going to talk about the interpretation of the master equation and in particular of the jump operators. And now you will understand why we call them jump operators. Okay, so first of all, we are going to consider just a single jump operator. So we will put J equal to 1. Okay, so J, it has only one J and one kappa. And we will take a Hamiltonian that is time independent, okay? But everything can be generalized trivially. It's just for simplicity now. So let me define, and let me maybe motivate it first. So you see that this equation here, it has a commutator, and then it has this term that is not a commutator, but actually, you see that this part in here, so J dagger J rho J dagger J, this is actually an anti-commutator, okay? So you see that it's an anti-commutator. So this means that if I define a new effective Hamiltonian that is non-Hermitian, so it has an imaginary part. So this is not a Hamiltonian, this is just, so let me call it effective non-Hermitian Hamiltonian. And I call it non-Hermitian Hamiltonian, but this of course is not a Hamiltonian because it's not Hermitian. So it's just a mathematical definition. But this allows me to write the master equation in a more compact form. which is this one here, that the time derivative of the state is equal to 1 over IH bar. Then we have something similar to the commutator. So it's just the effective Hamiltonian rho minus rho, the effective Hamiltonian dagger. Okay, you can check that this is true. And then we have a term that we cannot do anything with it to write it in any kind of commutator form, which is J rho J dagger. Okay? And now what I am going to show you, is that, well, obviously you see that the time evolution of the state has two very well differentiated terms. One is this term in here, and another one is this term in here. And what I am going to show you is that this term in here gives rise to reversible evolution. Okay, so this term is reversible. I can always revert something, so I can do something in my system to no matter what was the initial state that I don't even know. I can always do that in the system and then revert it back after some time to the original state. But this part in here, it's actually irreversible evolution. Okay? Irreversible evolution means that this part in here, if I just let it act, after some time, no matter what is the state I have at the beginning and what state I have at the end, I can do nothing, absolutely nothing, to come back to the original state, okay? Nothing, and you will see. Nothing other than to know what was the original state and then prepare it again. But I cannot just change something in my system such that it comes back easily to the original state. And in order to show that this is the case, okay, I will show you that this master equation is equivalent to the following kind of computational protocol. So consider the following protocol. To generate so rho at time t plus dt, and later on dt will be very small, from rho of t. Okay, so imagine we have rho of t. Now we want to find rho in the next step, t plus dt. And I tell you that we do it in the following way. So the following way is that, so I am an experimentalist, I have my lab, and then I decide to do the following protocol. With some probability, so with probability P of t, and this P of t will have a very specific form. So the probability is 2 kappa dt, and then the expectation value of j dagger j, of course at time t, okay? We apply what we call a jump, okay? And this jump means that we take the state rho and we transform it in the lab. So we apply a jump, means that we transform it into applying j to the state. So we have the state at time t and we apply it j. So if it's a pure state, it means that you just have j acting on the state. If it's a mixed state, then you have j and j dagger, okay, acting on the left and the right. And then of course, because this is not a normalized state, the state after doing this operation, this jump operation, will be this divided by the trace. Okay? So this is one thing. So imagine there is an experimentalist with probability P of t. It makes this operation. It applies a jump. And then with the the complementary probability, 1 minus P, okay, we apply, or the experimentalist applies, the following operation. It applies an evolution given by this effective time evolution operator that we just define as the evolution operator associated to the effective Hamiltonian. Okay? So this means that starting from rho of t, then with probability 1 minus p, we apply the evolution given by this time evolution operator, which is not unitary because the Hamiltonian is not Hermitian. So this might be more or less difficult to do in the lab, okay? But mathematically it's very well defined, and conceptually it will be very interesting. You will see in a second why. Okay? And now it comes the most important point. So I will show you in a second that this is completely equivalent to the evolution induced by the master equation. But for now, just believe that. And now it comes the important point. This thing in here is clearly reversible. So let me call it rho reversible. So when you apply this operation in here, what you end up with is something that you can undo. Why? Because I can always apply the inverse, the inverse of this operator, which is just changing t by minus t, okay? And then if I apply it to this reversible part of the state, I will go back to the original state, okay? So just think about it. It's just applying the inverse of this. That is very simple. It's changing t by minus t, and then I get it, okay? Because this operator has an inverse. It always has an inverse. So I can always apply it in the lab. On the other hand, this part in here, this is not reversible. So let me call it irreversible. Why? You can understand it very easily, because to reverse this evolution, I would need to apply the inverse of this operation. Okay, this jump operator. But in general, jump operators do not have an inverse. Okay, for example, we have seen the jump operator A, the annihilation operator. So this means that you apply the annihilation operator to your state, you remove one photon from your state, okay? Now you could think that the only thing that you need to do to invert the process is add a photon, but that's not true. The inverse of A is not A dagger, okay? A with A dagger is not equal to 1. And that's kind of clear, because when you apply a photon, so when you apply an annihilation operator, you will always, if you write it in the Fock basis, you will always get square root of n minus 1 for the Fock state. And when you apply A dagger, you will get square root of n plus 1 n. So what you end up with is not the original Fock state, but the original Fock state multiplied by n and n plus 1 in a square root. So then, in other words, this operation in here, okay, this operation cannot be inverted. You cannot invert it. While this operation here, you can invert it very easily, okay? So if you don't know what is the original state, if you apply this operation, you cannot come back to it ever again. If you know it, of course, you can prepare it again. You can do something in the lab to prepare the state that you were in. But if you don't know it, then you cannot prepare it just by doing an operation on the state that you get. So this is the difference between irreversible physics and reversible physics. okay? So now you understand why this operator is called quantum jump operator, because this operator, or if you want this part of the evolution, that is the one that determines this kind of process, is equivalent to applying something that is irreversible to the state, and we call that a quantum jump. It's something that you cannot predict when it happens. It happens just with some probability, okay? And when it happens, you cannot undo it. So it means that the system randomly has a jump, a quantum jump, that you cannot undo, okay? That's the meaning of quantum jump. Actually, during many decades, okay, there was the debate of whether these quantum jumps are something physical or not, okay? And like with many other things of quantum mechanics, the father of quantum mechanics and the fathers who invented all this quantum open system business and so on, long time ago, they thought that it's an irrelevant question. This is just mathematics, okay? You can understand it this way, but you will never be able in the lab of observing quantum jumps because this is a very microscopic process, blah, 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 that requires monitoring the system at very short time scales and so on. So, of course, as everything in quantum mechanics, now we can do experiments in this regime and we see quantum jumps in the lab all the time, okay? Well, not all the time. You have to really work hard to create an environment where you can see quantum jumps. So a lab that doesn't have classical noise and so on, so that you can see the quantum jumps. But we see it very easily in the lab nowadays. So then let me just show you, now that we understand this, let me just show you, the proof is very simple, how this protocol in here is exactly equivalent to the master equation. And the idea is very simple. So you know what are mixed states. So you know that if I tell you that with some probability you have this state, and with some other probability you have this state, the state of the system at time t plus dt will just be the mixture of these two possibilities, because we already studied mixed states, and we know that this is the definition of mixed state. So let me just show that this protocol is equivalent to the master equation. And this we do just by composing the mixed state of the protocol. So at time t plus dt, the state will be, with probability p of t, the irreversible state, and with probability 1 minus p, the reversible state. Okay? Now, it's very simple to write this thing. So this thing, it's equal. I write approximately equal because you will see why in a second. But let me write down explicitly the probability. The probability is 2 kappa dt expectation value of j dagger j. And what is the irreversible part of the state? Is the quantum jump applied on rho, and then divided by the trace of this. But what is the trace of this? Let me go back here. So the trace of this, because I have the cyclic property of the trace, I can bring this j dagger to this side, and then I get the trace of j dagger j rho. But that's precisely the definition of expectation value of j dagger j. Okay? So then you see that this expectation value with this goes away. Great. And then now we have the part of the irreversible state. So I will not expand this probability, I don't need it. But then the reversible part of the state, I remind you, is just this exponential. So this exponential acting on rho times the exponential dagger. But here it's where the thing, oh, sorry, I made one mistake. So So this is a time evolution operator, fine. But of course, the evolution that we apply is during a time dt. So please change this in your notes. If you are taking notes, this is the time evolution during time dt. Okay. Yes, Jinan?
The screen is locked, I think. We are still viewing the last PPT.
So you don't see the laser pointer now?
Right.
Okay. So let me see what happened. Let me stop sharing and I start again. So weird. So do you see it now? Do you see the laser pointer?
No.
Or, some people say yes.
I can see the laser flash, but in the last minute, we can see what you are writing. It's still in the last page.
I'm so confused. Yeah, but so now you see the laser pointer, right?
Yes.
So then now it's fine. Now it should be okay. You can see that here I wrote dt. Do you see it?
Yes.
Yes.
Okay. So before this was t, and what I said is that I made the mistake that this is the time evolution operator associated to the effective Hamiltonian, but here we are applying the evolution only during a time dt because we go from t to t plus dt. Okay. So this is the form, and then you see my new slide now.
Yeah. Yes.
Okay. So now, because dt is going to be infinitesimal, so this is the approximation that I am writing here. Oops. So dt, it's way smaller than 1. Okay, so it's an infinitesimal number. Then this exponential of dt, I can expand it as 1 plus, let me, just to make sure I don't make mistakes of signs, dt divided by IH bar, and then the effective Hamiltonian acting on rho, and then in here, 1 minus dt IH bar, and the effective Hamiltonian dagger, because this is the exponential dagger. Okay? And then in here, I have the same thing, but now, well, you can see it here, that just as before, we have here this U dagger. I can bring it, and of course, this is also U dagger of dt. So this is dt, okay? Then this U dagger, I can bring it to the leftmost sides and then I get the expectation value of U dagger U. So here I get the expectation value of, and now I do the expansion, 1 minus dt divided IH bar. And let me write H effective explicitly. I remind you that H effective, it's 1 minus I kappa, sorry, here I will get plus because this is the dagger, U dagger, then J dagger J, and then multiplied by 1 plus dt IH bar, and then the Hamiltonian minus I kappa J dagger J. This expectation value. So maybe let me make it a bit more clear. Okay, so now it's very simple to expand this thing. So first of all, this thing in here, this, if you just keep terms up to order dt, this is, we get the 1, then we get the multiplication of this times 1, and then plus this times 1. But you see that the Hamiltonian term goes away. because it has a minus and here a plus, while the non-Hermitian part, so the imaginary part, remains because we have minus I and minus I. So then in total, this thing in here is just 1 minus 2 kappa dt expectation value of j dagger j. Okay, but this is precisely 1 minus p of t. So you see that we have 1 minus p in the numerator, 1 minus p in the denominator. And then on the other hand, all this term in here, if we expand up to, again, first order in dt, this is equal to rho, and then plus dt divided IH bar, and then we have the Hamiltonian acting on rho minus the Hamiltonian dagger, sorry, rho acting on the Hamiltonian dagger. Okay? So in total, at the end, we have something like this, rho of t that comes from here, then the Hamiltonian part, and then we have the first part, which is 2 kappa dt j rho j dagger. Okay, but what is this? This is exactly the master equation. If you want infinite differences, or if you prefer, if you just take this rho t to the other side, and then you have rho of t plus dt minus rho of t, and you divide everything by dt, okay? Then what is in the right is on the left, sorry, is the time derivative of rho. And what is on the left, it's exactly what we have written here. Okay? So then you understand now, and this is the point of all this proof. I just want you to understand that the master equation has a reversible part and an irreversible part. And the terms that we get with the master equation formalism and with this tracing out the environment are precisely have this meaning of quantum jumps, okay? So perhaps you have already worked with master equations sometimes, or you have worked with dissipation in your research, in your internships or whatever, and perhaps someone has told you sometimes that dissipation in quantum mechanics is equivalent to a non-Hermitian Hamiltonian of this type, okay? Now you know that this is not exactly true. This is only true if you neglect quantum jumps, okay? Which you can do only as long as this probability of a jump remains almost zero, okay? And in that case, we say that we are in the classical limit of the dissipation or the classical limit of the open system, because we are neglecting the really quantum mechanical part of the open system, which is quantum jumps, okay? So this is just some terminology and some things that if you work in this subject, they will become very, very important. And many people make this kind of, I wouldn't call them mistakes, but it's just things that are a bit deeper that are sometimes not written very carefully in books, and then people don't think about it much. So now you know exactly the meaning of the master equation and the meaning of quantum jumps. So you will have all these discussions in the notes, so don't worry too much about writing this down and so on. And these are very technical things that I will probably not ask about in a lot of detail in the exam. So you don't need to know all the derivations, but just the general concepts. Okay, so then if all this is clear, so I hope that I made a case for reversibility and irreversibility. Then what we are going to do now is we are going to apply the master equation formalism to one example, which is the same example as we did in the Heisenberg picture, the driven empty cavity. And we have only 10 minutes left. So then what I will do is I will just show you the first part of that we need for this example, because the first thing that we will do is move to a new picture. So I will just show you how to move to this new picture in the master equation formalism. So then let me start with explaining how to change pictures in a master equation. Okay, so we already know how to change pictures. How to change picture means that we want to find out what is the time evolution. So what is the evolution equation of a new state of the system that is just the old state of the system, so the state that we know, whose evolution equation we know, and then we transform it with some unitary transformation that we like. In particular, we discount the evolution given by this operator UC of t. So this is a unitary operator. Then it's very simple, like we did for the case of just a Hamiltonian system, of a system that evolves according to the von Neumann equation. In this case, we get exactly the same kind of transformation. So we will get that the time evolution of the state in this intermediate picture is the intermediate Hamiltonian so the commutator, so the von Neumann equation with this. And of course, this intermediate Hamiltonian is the one that we have already written many times. That is just the transformation of the Hamiltonian, of the original Hamiltonian, that maybe even dependent on time, with discounting this evolution, minus IH bar, and then U dagger, and the time derivative of U. Okay, so this is exactly the same as we already knew. And now the only thing that is left is how do we transform the irreversible part, or if you want, the part that contains the quantum jumps. So again, this will be the same form. It's a dissipator. And now the only difference, if you take a look at the equation, so let me take a generic equation like this one, okay? So the only thing that changes when you want to evaluate the time derivative of the operator in the intermediate picture. So let me maybe put here, if I would just want the time derivative of the intermediate picture, what I would get is the time derivative of the state, okay? And then U and U dagger on each side, okay? So just from the definition. So the time derivative of the state in the intermediate picture will be the terms that have the time derivative of the state, that's contained already in the Hamiltonian, and then the time derivative of rho. But the time derivative of rho now is not only the Hamiltonian part, it's also the dissipative part. And the dissipative part, I can always write it like it was before. So here we will have the jump operators J, and this will be acting on the intermediate picture state. But now these operators J will be transformed, okay? So let me call them J in the interaction in the intermediate picture, and they might depend on time. Okay, so it's the same form, but now with new operators, new jump operators in the intermediate picture, which are just, as you can imagine, the transform operators. Okay, so the master equation takes exactly the same form as we had. So this form in here, just replacing the Hamiltonian by the Hamiltonian in the new picture, and replacing the jump operators by the jump operators transformed through the changing operation. Okay? So this is the first thing I want to tell you just about changing picture in a master equation. It looks very simple. And then the second thing I want to tell you, let me see if I have time, 8 minutes. I think it will take a bit longer than that. So maybe it's better that we stop in here. And we start in the next lecture from this kind of change of picture in master equations, and then we will consider this example, okay? But I think I will not continue. And I hope that even though it was a bit of a technical class, because it has a lot of technical derivations, it has a lot of physics, in particular physics of the interaction between system and environment, and under which conditions the environment will be easily traced out, and then you will find an equation for the system only. So I hope that now you are much more familiar with this thing. And please, I know that you might have many questions about this kind of physics. So just ask me any questions that you want, either now or after the lecture anytime. So, but for now, I will just say goodbye, and I will stay here for the next 10 minutes or so. So if you have any question, feel free to ask me. Otherwise, I will see you next week, and we continue with this chapter of open systems. So let me stop recording.